Welcome to ReneEnergy.com on YouTube, the hub for all things renewable energy and sustainability. Our channel is dedicated to bringing you the latest innovations and insights in green energy, including cutting-edge developments like green hydrogen. Whether you're a sustainability veteran or just beginning your journey, we have something for everyone. Join us on this channel to explore inspiring projects for a sustainable tomorrow. We bring you the latest in renewable energy, sustainability, and cutting-edge technologies. And don't forget, for more in-depth information and resources, visit our website and subscribe to our newsletter for the latest updates and exclusive content.
In the race to make green hydrogen a mainstream energy solution, one of the most overlooked but absolutely critical components is the membrane inside the electrolyzer. These thin layers of engineered materials serve as the heart of the hydrogen production process. But here's the catch. How long can these membranes actually last? Can they survive the 10,000-hour mark that many experts believe is necessary for long-term commercial viability? Today, we're diving deep into the science of membrane durability, why it matters, and what the future holds for the materials that are quite literally holding the hydrogen economy together. To understand why membrane durability is such a big deal, we first need to understand the role of membranes in water electrolysis. Whether you're using a proton exchange membrane, PEM, an anion exchange membrane, AEM, or even a solid oxide electrolysis cell, SOEC, the membrane is responsible for allowing specific ions to pass through while keeping the generated hydrogen and oxygen gases apart. That selectivity is key to maintaining safety, efficiency, and long-term stability. If a membrane degrades or fails, the entire electrolyzer system becomes compromised, leading to gas crossover, energy losses, and even potential safety hazards. Durability, in this context, refers to the membrane's ability to perform consistently under electrochemical stress, thermal cycling, and chemical exposure over thousands of hours. And the magic number that the industry is aiming for: 10,000 hours of operation. That's equivalent to running continuously for over a year. For utility-scale hydrogen production, this is considered the minimum viable lifespan before membranes should require replacement. Anything less than that starts to become a maintenance headache and a financial liability. Traditional PEM electrolyzers use membranes made from perfluorosulfonic acid polymers, Nafion being the most well-known brand. These membranes offer excellent proton conductivity and chemical stability, but they're not invincible. Over time, they suffer from mechanical fatigue, chemical degradation from radicals generated during electrolysis, and thinning due to hydration and dehydration cycles. These factors lead to performance loss and ultimately failure. Researchers have found that under harsh operating conditions, such as high current densities and elevated temperatures, Nafion membranes can fall short of the 10,000-hour mark, especially if they're not well protected by system-level controls. Anion exchange membranes, AEMs, which are gaining popularity for their use of non-precious metal catalysts, face their own unique challenges. AEMs generally consist of hydrocarbon-based polymers that are functionalized with quaternary ammonium groups to facilitate hydroxide ion transport. While this opens the door for cost reductions, these membranes are more chemically vulnerable in alkaline environments. The quaternary ammonium groups tend to degrade over time, especially when exposed to high temperatures and concentrated hydroxide ions. This degradation shortens the membrane's lifespan, and most AEMs are still in the process of reaching the durability standards set by PM systems. The problem of membrane durability is multifaceted. Mechanical degradation occurs when membranes are subjected to repeated swelling and shrinking cycles due to hydration changes. This leads to the formation of microcracks or pinholes. Chemical degradation is driven by reactive oxygen species that attack the polymer backbone. Thermal stress can weaken the structural integrity of the membrane over time. These issues are not isolated. They often occur simultaneously and compound one another, making durability one of the toughest engineering problems to solve in electrolyzer design. So, what are researchers and companies doing to push membrane lifespans beyond the 10,000-hour mark? The first approach is material innovation. Scientists are developing reinforced membranes that incorporate chemically stable backbones like aryline ether, or aromatic polyimides. These materials are inherently more resistant to oxidation and thermal degradation. Some membranes are being embedded with inorganic fillers, such as zirconium oxide or silica nanoparticles, to enhance dimensional stability and reduce swelling. Another promising route is the development of composite membranes. These combine different polymer chemistries to balance conductivity with mechanical robustness. For example, hybrid PM-AM membranes are being explored to blend the benefits of both systems. These membranes aim to provide higher ion selectivity, lower gas crossover, and improved resistance to degradation. In the world of AEMs, researchers are working to develop novel cationic groups that are more stable than traditional quaternary ammonium compounds. For instance, imidazolium, phosphonium, and guanidinium groups have shown promise in resisting alkaline attack while still maintaining high ion conductivity. These developments could be crucial in pushing AEM membranes past the 10,000-hour threshold. Beyond materials, operational strategies also play a crucial role in membrane durability. Maintaining optimal hydration levels, avoiding extreme current densities, and controlling temperature can extend membrane life. Advanced system designs are being introduced to provide real-time monitoring and feedback, adjusting parameters dynamically to prevent conditions that accelerate degradation. Some companies are even using AI and machine learning to predict membrane failure before it happens, allowing for preemptive maintenance. Testing protocols are also evolving. Accelerated stress testing, AST methods are being used to simulate years of membrane operation in just weeks. These tests expose membranes to elevated temperatures, voltages, and aggressive chemicals to predict how long they'll last in the field. The data gathered helps improve both the materials and the systems that support them. So who is leading the charge when it comes to long-lasting membranes? In the PEM space, companies like Gore and 3M are continuously refining their membranes for higher durability. Gore's advanced reinforced membranes, for instance, have shown lifespans exceeding 10,000 hours in some applications. In the AEM world, companies like Versogen and Enapter are at the forefront of pushing membrane performance closer to commercial viability. Enapter's modular AEM electrolyzers are designed for distributed hydrogen production and are undergoing long-term durability testing to ensure they can meet or exceed industry benchmarks. Research institutions like the National Renewable Energy Laboratory, NREL, the Fraunhofer Institute, and the Japan National Institute of Advanced Industrial Science and Technology are publishing groundbreaking research on membrane durability. These institutions often collaborate with industrial partners to test membranes under real-world conditions, bridging the gap between lab performance and commercial reality. Durability is not just about cost, it's about confidence. Companies investing in electrolyzer systems want to know that their equipment will last. Governments backing hydrogen strategies want technologies that are dependable. And the broader clean energy market wants assurances that green hydrogen can deliver consistent, affordable results over the long term. Membrane durability is at the core of that confidence. We're not quite there yet, but we're getting close. The 10,000-hour barrier is not just a dream, it's a realistic goal, thanks to the incredible amount of innovation happening in materials science, electrochemistry, and systems engineering. As membranes become more robust and systems smarter, the hydrogen economy becomes more viable. We may even begin to see membranes that last 20,000 or even 30,000 hours in the near future, drastically reducing the levelized cost of hydrogen and opening new markets that were previously out of reach. So, can today's membranes survive 10,000 hours? Some already can under ideal conditions, and many more are on the way. The next few years will be pivotal as these membranes move from the lab to full-scale commercial deployment. It's not just about surviving, it's about thriving under the conditions required to power the next generation of energy systems. What do you think? Is membrane durability the final bottleneck before green hydrogen takes off? Or will new breakthroughs push us past this barrier even faster than expected? Drop your thoughts in the comments. And if you found this deep dive valuable, don't forget to like, subscribe, and hit the bell icon so you won't miss our upcoming episodes on hydrogen technology and clean energy innovation. See you in the next video!
Thanks for tuning into the ReneEnergy.com YouTube channel. We trust you found this episode enlightening and motivating. There's a world of innovation and opportunity in sustainable energy, and we're delighted to share this journey with you. Stay in the loop with the latest on renewable energy and sustainability by visiting our website and subscribing to our newsletter. Your support is immensely appreciated, it's truly invaluable to us. Don't miss our next video on new trends in renewable energy. Follow us on social media for the latest updates. Enjoyed the video? Like, subscribe, and share for more green insights. Thanks for watching.